There are three different types of chemical bonds that are in the category of major types of chemical bonds. And the first one is when you have a metal atom bonded to another metal atom, such as iron bonded to itself. And these are simply referred to as metallic bonds. And that is one category. We aren't going to talk about this category much in this course, but they tend to easily conduct electricity. The next category is when you have a metal bonded to a nonmetal, such as sodium bonded to fluorine, okay, metal, nonmetal, and those are ionic bonds. And those form compounds. Remember, compounds are bonded species that have more than one different atom, and of course if you have a metal and a nonmetal they would have to be different. All right, and in this case you have, in ionic bonds, one of the species gives electrons and the other one takes electrons. So you have give and take. Then the third category is nonmetal bonded to a nonmetal. So that could be, for instance, carbon and hydrogen. It could also be hydrogen bonded to itself. And those are covalent bonds. And in covalent bonds, there's not giving and taking, but there is sharing of electrons. All right, and when we have nonmetal bonded to nonmetal, we call these molecules. And some elements exist as molecules in the natural state. So I'll give you some examples of elements that exist as molecules in their natural state. That includes hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, iodine, and there are more. But those are some you should be aware of. All right, so remember when you look at the periodic table, you have metals. All of the group 1A and 2A are metals. The transition metals are metals, and everything to the left of this zigzag line is a metal, with an exception. Okay, the exception is hydrogen. Hydrogen is actually a non-metal, but it usually appears on this side of the periodic table. All right, so all the other non-metals are on this side of the periodic table. So you can look at the periodic table, see what's bonding to what, and identify it as ionic or covalent based on that. And the main group elements, okay, main group means this area and this area. The main group elements will form compounds that leave them with 8 outer shell electrons, and this is known as the octet rule. Okay, they have 8, an octet, and the transition metals do not do that. So that is the octet rule. All right, now we're going to focus specifically on ionic bonds. So we're talking about ionic bonds first, and that you remember is between a metal and a nonmetal. And the metal becomes a cation, which is positively charged, and the anion, and the nonmetal becomes an anion, which is negatively charged. So in order to become a cation, the metal had to lose electrons. Okay, because it is positively charged, that is because it has the same number of protons in its nucleus, but it has lost electrons, so the overall charge is now positive. The anion, to get there, has gained electrons. All right, so let's look at an example, sodium and chlorine. Sodium's electron configuration is neon core and a 3s1 electron. Chlorine's electron configuration is neon, 3s2, 3p5. So when sodium and chlorine form an ionic compound, the sodium loses 1 electron, its valence electron, and that valence electron gets transferred over to the chlorine, who gains 1 electron. Okay, so when the sodium loses that electron, its configuration is simply neon. And when chlorine gains an electron, its configuration is now neon 3s2 3p6, and that is the same thing as argon. So it now has a noble gas configuration as well. And so sodium and chlorine both have a noble gas configuration, and the chlorine is negatively charged because it has one more electron than its number of protons in the nucleus. The sodium is positively charged because it has one less electrons than the number of protons in the nucleus. And it forms the compound sodium chloride, which we don't write the charges in because the positive sodium is attracted to the negative chlorine, and they form a bond. All right, so let's look at another example. Magnesium has the electron configuration neon 3s2. Okay, so it has two valence electrons, unlike sodium, which had one. Fluorine has the electron configuration helium 2s2 2p5, and we can put in another helium. I'll tell you why. 2s2 2p5. All right, because magnesium has two valence electrons to get rid of, it can give it can get rid of one electron to this fluorine, and it will have a noble gas configuration, but it can give another electron to this fluorine, and then it will have a noble gas configuration. So the fluorine will have a neon configuration, the magnesium will have a neon configuration, and then the other fluorine will have a neon configuration. So when magnesium and fluorine form an ionic compound, it's in a 2-to-1 ratio so that the charges are balanced. The 2 plus is balanced with 2 separate minus charges, and you get the compound magnesium fluoride, MgF2. Okay, so we can summarize this by looking at the periodic table and seeing what kind of ions are formed. And we're talking about the main group, which means we're not talking about the transition metals at all. We're just talking about groups, the A groups. All right, so the 1A and 2A groups form cations. They lose electrons. 1A forms a 1 plus charge. Group 2A forms a 2 plus charge because that's how many valence electrons they have. Group 3A metals will form a 3 plus charge. If we look at the nonmetals, so that's above your zigzag line here, the nonmetals will form anions, and when they are one column away from the noble gases, they'll have a -1 charge. When they're 2 columns away, they'll have a -2, and when they're 3 columns away, they'll have a -3. So those form the anions. All right, let's do some practice. Which ions will the following form when making ionic bonds? So pause the video when you need to answer these questions. We answer it by looking at the noble gas, or looking at the electron configuration. Okay, calcium's configuration, argon, 4s2. It will want to lose, it's a metal, so it's going to want to lose those 2 valence electrons, which means its configuration will then be argon, and when it loses 2 electrons, it becomes calcium 2 plus, because it still has the same number of protons in the nucleus. Sulfur has a configuration neon 3s2 3p4. It's a nonmetal, so it's going to gain electrons, and it's 2 away from having a full p subshell, which would give it an argon configuration. So it's going to gain 2 electrons and become S2 minus. Potassium has argon 4s1, has 1 valence electron. It's a metal. It's going to lose that electron and become K plus with an argon electron configuration. And finally, bromine has a configuration argon 4s2 4p5. It's 1 away from a noble gas. The noble gas would be krypton, so it's going to form Br minus. All right, now let's use those results to predict which of the following ionic compounds are impossible. Okay, so let's look at one at a time. calcium and potassium. Calcium is 2 plus, potassium is 1 plus. That's 2 cations. They are not going to form an ionic bond. They're both positive. So this is 1. This is not going to form a compound. Calcium and bromine. Calcium is positive, 2 plus. Bromine is 1 minus. They are opposite, okay, one's plus, one's minus, but the magnitude is different. So when you have 2 plus in the calciums, you'll need 2 bromines that are 1 minus, and that's exactly what we have. So this is a valid compound. Let's look at Ks. Potassium, 1 plus, sulfur, 2 minus. They are opposite charges, but the magnitudes are not the same, so they can't form a 1-to-1 ratio. This one is not possible either. Let's look at K2S. Again, they're opposite, and 2 potassiums will make 2 positive charges. That will balance the 2 minus charges. That one is valid. So let's look at some general rules for forming ions to make ionic bonds. In the S block, okay, the S block is 1A and 2A metals, right? You will remove all S electrons in the outer N level. So that's the valence level. So for example, your sodium will become sodium plus, your strontium will become strontium 2 plus. Sodium has 1 valence electron, strontium has 2. In the P block metals, now we'll do P block nonmetals in a minute, but in the P block metals, you're going to remove the P electrons, and then you're going to remove the S electrons if needed. In the lower rows, you will always remove both. So in the lower periods, you'll remove all, NP and S. So for example, aluminum will become aluminum 3 plus. That's in the P block. But in the lower levels, for example, lead, if you look where lead is on the periodic table, it would have an awful lot of electrons to remove the entire row. It tends to remove 2 or sometimes 4 electrons. So you remove the P electrons first, and then if you're going to remove more electrons, you move the S. All right, the D block, transition metals, you're going to remove the S electrons first, and then some of the D electrons if necessary. So the S electrons are going to be in the outer N level, but the D electrons in that same row would always be 1 less in N. So for instance, manganese becomes manganese 2 plus. And when you make it 2 plus, you take away the S electrons, not the D electrons. And also iron. Iron becomes iron 2 plus by removing just the S electrons, but it also can become iron 3 plus by removing 1 of the D electrons. All right, and finally, the nonmetals. Those are going to gain electrons, right, not lose. So you're going to add electrons to fill up the NP level and therefore give it an octet. All right, so for example, sulfur, which we've just done, is 2 away from the noble gases. So to fill the p orbitals, we would give it 2 more electrons, so it would be 2 minus in the charge.